Okay, we'll continue with the false path discussion. As we had seen earlier, the computation of the critical path is not merely structural, it does depend on the logic and what else is going on in the rest of the logic and not just what is happening on the critical path. The actual critical path may be different from what a structural traversal of the graph might indicate, and in general it is necessary to examine the logic. So, let us just try to arrive at the condition that determines a critical path, so that one could make it a part of the analysis. The basic question then is related to the propagation of an event. When does an event propagate along a path? For that, one definition is worth noting, because the condition could be nicely captured in terms of this function called a Boolean difference. So, suppose you have a function f of 3 variables. So, this is an AND gate with f as the output and ABC as the function inputs. So, that is the normal output ABC, which is 1 when all the 3 are 1, otherwise it is 0. Let us define the Boolean difference operator as follows. Boolean difference of a function with respect to one of its input variables is defined as that function if you substitute a equals 0 XOR that function when you substitute a equals 1. It means f of a XOR f, if you just replace the a's by a prime in the function. In this example here, f of a is just this, f of a prime is if you replace a by a prime, then that entry becomes 1, because the a's and the a primes get inverted. So, where you had a 1 earlier you have a 0, and where you had a 0 earlier you have 1. So, that is the logic for a prime B C, that is the column, truth table column for a prime B C. XOR of these two columns gives this column where these two are different and these two entries are different, everywhere else it is 0. That is our function called a Boolean difference. Boolean difference of a function is defined with respect to its inputs, with respect to one of its inputs. That is what the a is, it is one of the input variables of the function. Okay. What does this tell us? If this was 0 throughout, what does it mean? This is an XOR function, and if an XOR function is 0, it means that
both the entries are same.
Both the entries are same. What is the meaning both the entries are same here? What does that mean?
That means it does not matter if a is 0.
Doesn't matter. You put a equal to 0, you put a equal to 1. If there is no difference, then that function is independent of a. Okay. What if it was 1?
Then it is dependent on the a somehow, because
it is dependent on a. What else can we say? In general, Boolean difference is a function. These are just two extremes. In general, what is a Boolean difference? When you do an XOR, as it is here, what is the Boolean difference actually here? It is neither 0 nor 1. This is a column that consists of both zeros and 1s. So, what is that difference?
It is an OR of the two, in a way.
It is just another function, right? So, what function is it of a, b and c?
It has become an OR of a plus b plus c plus a prime b c. Basically it has become b c.
It has become b c. Right, it is B C because it is a prime B C plus A B C, which is just B C. Does that make sense? What would it mean? If B C is the Boolean difference, what are we saying?
We eliminate eliminated A.
A is eliminated, yeah.
And we
That's
learned that elimination of A gets us a different function. It is no longer, basically, it's not redundant. That literal has a.
A is certainly not redundant as far as the function is concerned. So, if it's 0, it means that it is actually redundant, the function is independent of A. If it is 1, it means that, what does it mean? That function is actually f of A prime XOR f of A. If it is 1, it means that f of A prime is always different from f of 1 is the inversion of the other.
Does it mean that it is only dependent?
That is the other extreme, that it is dependent only on A.
At that.
But in general, this is a function, and that function, the Boolean difference, if you ensure it to be 1, for example, you set the input variable such that that Boolean difference is 1, then the function, any change that you make in A becomes visible at the output of the function.
Can you please repeat this?
So, this is BC, right. So, if BC is equal to 1 here, what is this function anyway? This function is ABC, right. If you hold BC as 1, it means that changes in A are reflected directly in the changes in the output of the function. That is what the Boolean difference captures for us. It is an important metric, as we say, it will help in establishing sensitization of a path, right. It establishes that you hold the other inputs of the function to whatever values in a way that your path is actually sensitized. The specific input that we want, that is the input with respect to which we take Boolean difference. Right. So, this tells us what the other inputs should be, so that our changes at the input, at the A input, are reflected in changes in the output. Yeah.
The input patterns are provided using this function, which
We will get to how to apply it, but as of now, that is just the definition and an informal interpretation of what it might be.
can be in respect to a single variable only at a time.
This is with respect to a single variable. Although we have introduced this in the context of timing analysis, this has other interesting applications. If you were to do a power optimization of a combinational circuit, there too you are interested in, if an input changes, how far will it propagate in the circuit, right, because it may get masked at various other stages by values that do not allow that input change to propagate to the output. There too there are some interesting, in the analysis with respect to let us say power estimation, or even when you do power optimization, such a concept is useful in the theoretical formulation. Okay. So, but that is just remember that is the Boolean difference, we will use it in one context here. Yeah.
If any row in that table will appear as 1, that df by
Right.
the partial derivative will be, it is bound to happen that there will be another row which will be 1, because it will always happen in pair, because that is how it is.
XOR
Its difference, so yeah.
And is there a way to do that in code where I have an expression, I need not create the truth table,
This is the definition.
but I still need to get all the zeros, all the two.
No, you have one function, right? F of A prime is one function, Boolean function. This is another, f of A is another Boolean function. The XOR of these two, if we can take in an efficient way, that is what gives us the resulting function.
Okay. So
Right.
will you be covering that also? This
Covering
is,
what? So, we covered representation of Boolean functions.
Right.
Now, I need to manipulate that representation to perform ANDs and ORs and XORs and so on. BDDs could be used to achieve the basic operations. They are defined, we did not cover them. Actually, we left them saying you work it out.
Okay.
Remember, after we talked about the representation, I said that it may be an instructive exercise to just try and understand how you would do AND, how you would do OR. You have two different functions of the same or overlapping set of variables. How would you do AND? So two functions means you have done BDDs on the same data structure and they are pointing to different entries of that hash table. So the hash table is the same, it's just I have defined two different functions. How would you do AND? How would you do OR? It is non-trivial, it's not obvious. Try to do that yourself. The book does have the formal way of doing it, but XOR or any such operation, there is a standard way to do this. Getting back to this question of when does an event propagate along a path, an event propagates along a path P if the Boolean difference for all gates along the path, you see that is one of the gates, right. So, df by dg means for every gate along the path, the Boolean difference of the output with respect to the input that is there in the path,
has to be 1.
if that is true, it means that events on the input will propagate to the output. So, that is what we looked at. So, it defines the conditions for the rest of the inputs of the gate. So, if those conditions are true, then we have established the propagation of an event.
So what we have done is basically we have now a new function, and in that function wherever we have a 1, that's where the input patterns for which we will have a sensitized
Yes.
path.
Yes.
But sir, then again we will need to build a ROBTD for that.
Oh yeah, we are not saying this is trivial, and in fact the actual determination of the condition is still there. We have only defined what condition needs to hold for us to propagate the path, but we will get to that soon. So, couple of things. Static sensitization of a path is defined as follows. We say a path P is statically sensitizable if there is an assignment of the primary inputs such that Boolean difference is 1 for all the gates along the path. So, assignment of primary input means here some condition has to hold, right, for the other inputs. On that gate some condition has to hold on all the other inputs. These gates are not of that nature, but it is like this. To establish that path, you have to collect all of those conditions on the rest of the inputs of the gates. It is some function. So, ultimately you express that in terms of the primary inputs, right, all the primary inputs. That condition, if you are able to obtain an assignment of primary inputs such that all of those Boolean differences turn out to be true, then you have established the sensitization. This is what we call a static sensitization. This is actually independent of the delays of the gates themselves, assuming that once everything is stable, if this condition holds, then that path that we are interested in is sensitizable. Okay. That is not the only condition under which it is sensitizable, but if this is true, if this condition is true, then it is sensitizable. Okay. So, that is what is called as static sensitivity. Let us just define one more term that says a controlled value and a controlling value. For an AND gate, we say that a 0 is a controlling input value. What does it mean? It is just that if that value is 0 on one of the inputs, then irrespective of what is there on the other inputs, you know the output. Similarly, for an OR gate, the 1 is a controlling value, because once you have 1 on one of the inputs, then you do not care about the others. The output is forced in both the cases. So, that is what it is. So, there is this idea of a controlling input, and correspondingly there is a controlled value at the output, whatever that corresponding value is. When you have the controlling input, then the controlled value on the AND gate is 0, controlled value on the output of the OR gate, that would be 1. Static co-sensitization is defined in the following way. For a path P, it is statically co-sensitizable if there is an assignment of primary inputs such that for all the gates along the path, G has a controlling value whenever f has a controlled value. Means if this has 1, this is an output of an OR gate, if that is 1, then this has a 1. If it is this, what about the inverter? There is only one input. So, this question does not really arise, both values are controlling and controlled. So, that is what this is. G has a controlling value whenever f has control value. We are not saying anything about the other input, that is how it is different from the static sensitization. But in reality, of course, whether that path actually is sensitized or not does depend on what is happening on the other input. So, we have to formulate this a little further, but this is the definition, it is statically co-sensitizable if that condition holds. If a control value is there on the output, then the controlling value is there on the input of our interest, that forms the path. Okay. Then let us outline the path sensitization condition. If it is static sensitization, then everything is fine. We insist that all the other inputs on that gate should have non-controlling values, so that our path is sensitized. So, that is one possibility. If this condition is true, then it is fine, then it means that we have identified a sensitizable path. With the co-sensitization, I need to go a little further as follows. That is the path of our interest, right, and I say that it is okay for that other input to also have controlling inputs, but under the following conditions. If both of these have controlling inputs, right, both have zeros, then we want that along our path the controlling input should appear earlier. Then it does not matter that the other input also gets a controlling value, the change in the output is because of our input. Is the logic clear?
Sir, we only talk about a single change while sensitization.
Per edge.
What do you mean a single change? All edges here result in edges there on the output, right. So, both the edges. When we say path, it means that any change on the first input ultimately gets reflected on the output, no matter how long that path is. So, this is a relaxation. Instead of strictly insisting that all the other inputs must have non-controlling values, it could be that we allow a controlling value on the others also, but the timing situation is such that this signal arrives first. If it is a controlling value, then along our path of interest the controlling value must appear first. Then too we say that it is sensitizable. So, this is part of a co-sensitization. Correspondingly, it is okay for us to have both inputs being non-controlling, right, both of them being 1, but if that is the case, then we want our input to arrive later. You see, both of these are 1, you see that the output was 0 even here, it does not matter that the other inputs became 1 earlier. But this is the one that is going to make a difference. If this is going to make a difference there, then we want that even if the other inputs have non-controlling values, our input is non-controlling, even if the others have non-controlling, if ours is the last one, then you would still see that path being sensitized. This is an outline of what is a necessary condition for a critical path. That critical path, of course, is one that is sensitizable. Remember, we defined that critical path in 2 terms. One is it is the longest delay structurally, but also it should be sensitizable, right. If it is not sensitizable, it is a false path, and that is not the critical path. So, these conditions can be the additional conditions that could be imposed. This one, if it is true, it is fine. but otherwise combination of these two requirements can form the necessary condition for identifying a critical path.
Co-sensitization.
Co-sensitization just refers to that there is a relationship with the other inputs also. It's not
Used. Can you cite an example which where it is used in some process in the VLSI design?
this is a tighter determination of the critical path, right? So, what do you mean is it used? This is a timing analysis, is part of a timing analysis function. So, I could do just this, just the static sensitization, but it turns out that is too restrictive. This would be a way to relax that and actually have a more technically correct interpretation. Then the false path detection involves what things? We need to determine the set of input values that will allow a path sensitization, which means that we have picked one path and now we require a bunch of other functions to be true, right. All those Boolean differences need to be true, which means that essentially it is like you have the product of a bunch of expressions, those need to be true. How do you ensure those are true? You have to solve the satisfiability problem that ultimately assigns values to primary inputs such that these functions are all true. So, this of course is the classical Boolean satisfiability problem. Often manual inputs are used, the designer may have some intuition himself about which are the paths based on external knowledge, not necessarily obvious from the netlist itself, but other knowledge might be there that the designer can actually use to instruct the tool that these paths are false. So, that is about the false path. Let us quickly go through what is essentially just a definition and putting together. Once you have computed the critical paths through the combinational logic, what else remains to be done? So, that analysis was valid for combinational logic so far, but of course, real designs are sequential and there are flip flops along the way. How do you account for them? You need to, at a very basic level, of course, take into account some of the timing features of the flip flops themselves. What kind of timing features are there in a D flip flop? Things are defined with respect to the rising edge of clock, right. What are the timing parameters? There is the requirement that before a clock edge, that input must stabilize for a certain amount of time, that we call the setup time, right. It's this. So, before the, so if that is the clock edge, then the D input must be ready by this time, otherwise it will not be properly latched. So, that is one parameter we do need to take care of. There is a hold time which essentially requires us to keep that D input stable past the rising edge of the clock. So, it has to be stable for that much time, right, some time setup time before the clock edge and hold time beyond the clock edge. One other important timing parameter that is relevant for us is there is a delay from the time the clock rises to the time the output, the Q output stabilizes, called a clock to Q delay. So, at the very least these three timing parameters I must take care of. There is a further dependence on the actual value is 0, value is 1, the timings may be different, but at least these are these, you can take the max out of the different values if there is sensitivity with respect to the value. Let us say clock to Q may be different for Q equals 0 than for Q equal to 1. If it is, then you just take the max. So, at least these three I need to in a simple way capture in my formulation. Then what is the max delay constraint? If there is a clock period, then we require that whatever is the critical path of that combinational logic, I must account for that much delay for the clock to Q, because the inputs to that combinational logic may be coming from flip flop outputs. So, that output is ready only after that much time, right. So, that is one thing. Other thing is, whatever outputs we compute here may be D inputs of a flip flop, and therefore, I also need to complete before the setup time for a flip flop. So, my requirement could be that in addition to whatever is the critical path that I have computed, I have that propagation delay and that setup time. Together, all of this must be less than the clock period. Of course, this is still at a logical level. Remember, there are routing delays and other delays that complicate this further, but we can proceed in this direction. If there are other delays that we are able to analyze and incorporate, then that equation should have those also. What about the hold?
Sir, hold should be less than clock.
Hold should be less than clock period, that is fine.
Clock should be less than clock to Q.
Is there a relationship between the critical path? Just like we had one equation here, can we come up with a different equation involving the hold, or there is no need? There is, okay. So, then
T-hold should be less than contamination delay of logic and the contamination delay of clock to Q, the minimum delay.
the minimum delay of the logic, this critical path is essentially the max delay, but this propagation delay plus the minimum delay through this must be
Greater than a hold.
greater than the hold, right. So, such an equation also can be there. Normally, you may not have an issue, but if you do, then you may have to put some buffers or something like that to make sure that the hold time of which flip flop are we talking about here? This one, right, because that value has to stabilize for that much time. Yeah, fine. So, such computations ought to be part of the timing computation. What other extensions we can think of? Well, a lot of simplifications we made along the way. Gate delays are variable in the general case. Of course, there is a dependence on the output load, there is a dependence on the input slew, the rate at which the input is changing. Both of these do contribute to the gate delays in ways that are non-trivial, because they are not obviously known when you start off. The net list, if it is known, then at least partially the output load is known to us, because we can compute the load based on fan out, a certain model can be used. This information is necessarily partial, because the actual load is known only when your routing is complete. Without that, you have to make some assumptions. So, that is one thing, there is a variability. The rise time and the fall time might be unequal. Okay. These transitions might be unequal for a variety of reasons. It depends on the transistor types, it depends on so many other things. The timing characterization of the gates would usually have this information separately characterized. To simplify an analysis, you may just take max or min or whatever makes sense, but these delays are of course separately characterized. And as we have indicated in several places, there are wire delays might be significant, and therefore, the load due to the nets would need to be estimated in some way. Okay, that completes the discussion I had in mind for the timing analysis. Of course, it is a very short discussion. There are a lot of other things that we did not go into, but this is sort of a very elementary logic level discussion of the timing analysis problems. That completes the topics I had in mind for the synthesis course. We did manage to go through most of the topics that I wanted to cover. There was one that was left as optional, unfortunately. If I had a full class, I would have paid some attention to it. Those involved a couple of ideas from the physical synthesis. That is also synthesis, and we did not. While this is supposed to be synthesis of digital systems, the physical synthesis would involve things like place and route. Those, of course, are topics that are complex enough in themselves that they merit a separate course really, but nevertheless some of the basic ideas it is not hard to cover. But at a very elementary level, standard cell routing, what is involved, what is the objective function, and what kind of optimization is involved. It turns out that particularly standard cell routing, the problem and its solution has some very nice parallel analogy to some of the synthesis problems that we have already seen. There is also a global placement and global routing and so on. The elementary ideas involved there can certainly be discussed in a relatively small amount of time, but since this is sort of a logical break, I decided to skip those topics.